Hey there, and welcome. The world around us is constantly changing, transforming, and basically rewriting itself every single second. And the language it uses to do all this? Well, that's chemistry. Today, we're going to learn how to read that secret language, the hidden language of chemical reactions. So, let's kick things off with a little puzzle. Imagine you take a totally normal silvery iron nail and you just dip it into this bright blue liquid, a copper sulfate solution. You walk away, come back a bit later, and boom, the nail is covered in this brownish stuff, and the blue liquid, it's all faded out. It's almost like a magic trick, right? So what is really going on here? Well, the answer is there's a hidden chemical battle going on, a silent but pretty powerful fight happening at the atomic level. And here's the cool part. What's happening right here in this one little test tube is the key to this whole explainer. If we can figure this out, we've basically got the secret decoder ring for the entire language of chemistry.
All right, so first things first, we need to put on our detective hats. How do you even know when a chemical reaction, a real chemical change, has actually happened? Well, you have to look for the clues.
Think about it. Just like a detective hunts for evidence, scientists do the exact same thing. In this picture, for example, when some zinc gets dropped into acid, you can see it happen right before your eyes. Bubbles of hydrogen gas start fizzing up, and if you could touch that test tube, you'd feel it getting warm. These are the fingerprints of a reaction. They're screaming at you that the original stuff is being transformed into something totally new. So basically, you've got this mental checklist of 4 classic clues to look for. Is there a change in temperature? Are you seeing bubbles, a gas being formed? Is there a change in color, kind of like our iron nail turning brown? Or, and this one is really cool, are you seeing a solid form when you mix 2 liquids together, almost like magic dust appearing out of nowhere? That solid, by the way, has a name, a precipitate. If you spot any of these, chances are you're watching chemistry in action. Okay, so spotting a reaction, that's step 1. Check. But now, how do we actually talk about it? How do we write it down so any scientist anywhere on the planet knows exactly what we saw? We need a universal language, one with its own set of rules. The basic grammar here is actually super simple. The ingredients you start with, those are called the reactants. And the new stuff you end up with, those are the products. Reactants go on the left, products on the right. That's it. We could just write it all out in words. Sure, that works, but it's kind of long, right? That's why scientists came up with a shorthand, using symbols for each substance. We call it a skeletal equation. This is the universal code. And it's awesome because it packs in even more info, like those little letters and parentheses that tell us if something is a solid, a liquid, or a gas.
But here's the thing. In this whole language, there is one fundamental, unbreakable rule. Think of it like the most important rule in baking. You can't just create flour out of thin air. It's called the law of conservation of mass. And all it really says is that in any chemical reaction, you have to end up with the exact same number of atoms of each element that you started with. You can't just lose an atom somewhere, and you definitely can't create a new one. They just get rearranged into new patterns. Okay, keeping that law in your head, take a look at this. This is the equation for burning magnesium. Magnesium plus oxygen gives us magnesium oxide. You see it? Can you spot the problem? Where do we just break that big, unbreakable law? Let's do a quick head count, an atom inventory, and you'll see the problem right away. We start with 1 magnesium atom, we end with 1. Okay, we're good there, but we start with 2 oxygen atoms on the left side, and somehow we only end up with 1 on the right. An oxygen atom just vanished, which of course is impossible. So how do we fix this? Easy. It's a simple 3-step trick. 1, write down the basic equation. 2, count up all your atoms on both sides. And 3, this is the secret sauce. You use big numbers in front of the chemicals, called coefficients, to make the count equal on both sides. Now watch this. Just by adding a couple of simple numbers, these coefficients, everything just clicks into place. We put a 2 in front of the Mg and a 2 in front of the MgO, and suddenly our inventory is perfect. 2 magnesiums on the left, 2 on the right. 2 oxygens on the left, 2 on the right. Beautiful. The equation is now balanced. Our chemical sentence is correct. All right, now that we know how to write a proper, balanced chemical sentence, we can start seeing patterns. Turns out, just like sentences in a language, chemical reactions tend to fall into a few different categories. Let's look at the 4 big ones. First up, we've got a combination reaction.
This is about as straightforward as it gets. You take two or more separate things, let's call them A and B, and they combine to form one single, more complex thing, AB. A perfect example is iron and oxygen coming together over time to form a totally new substance, rust. And then you've got the total opposite of that, a decomposition reaction. Here you start with one complex thing, AB, and it breaks apart into its simpler pieces, A and B. A really dramatic example of this is an airbag in a car. One single chemical compound decomposes incredibly fast into nitrogen gas to inflate the bag in a split second. Next up is displacement, and this one is kind of like a dance partner swap. You've got element A, and it comes along and sees element B paired up with C. Well, A just cuts in, kicks B out, and forms a new pair, AC, leaving poor B all alone. And this brings us right back to where we started, our mystery in the test tube. It's a classic displacement reaction. The iron, which is more reactive, comes in, kicks the copper out of the copper sulfate, and takes its place. And that brown stuff coating the nail? Yep, that's the copper that just got kicked out. Mystery solved. And last but not least, we have double displacement. Think of this as a full-on partner swap for everyone. The ions in two different compounds all switch places to form two completely new partnerships. It's the kind of reaction that's actually used in water purification to get rid of unwanted minerals. Okay, but wait a second. That brings up a really important question. In our nail experiment, how did we know the iron was strong enough to kick the copper out? Why not the other way around? Well, it turns out that some elements are just naturally more reactive, and if we know who's who, we can actually predict whether a reaction will happen at all. Well, this is where the reactivity series comes in. It's basically a chemical pecking order, a ladder of strength. The metals at the very top, like potassium, are the heavy hitters, super reactive. The ones at the bottom, like gold, are pretty chill and unreactive. The rule is simple. Any element can displace another element that is below it on the ladder. Now, just look where iron is, and then find copper. Okay, so pop quiz time. Based on that ladder we just saw, what do you think would happen if we flipped our experiment? What if we put a copper wire into an iron sulfate solution? Is anything going to happen? And the answer is a big, fat no. Nothing happens. Copper is lower on the ladder than iron, which means it just isn't reactive enough. It's not strong enough to go in there and kick iron out of its compound. And this isn't just a party trick. This predictive power is huge. It's how engineers pick the right metals to stop ships from rusting or to build batteries that last longer. So there you have it. You now know the signs to look for, the grammar to write it all down, and even the rules that let you predict the future. This hidden language of chemistry, it's happening all around you, all the time, from a gate rusting in the rain to the bubbles fizzing in your soda. So the real question is, what hidden reactions are you going to uncover today?